Welcome back. In our last video or our last set of videos, we have looked at the concept of the complex number. We have also looked at ways in which you can add, subtract, multiply complex numbers together, divide complex numbers together, find the powers on complex numbers, as well as the roots of complex numbers. Now, we want to go into the concept of limits, continuity, and differentiability of a complex function. In order to do this, we will first and foremost need to properly define what the complex function is, and of course understand how that complex function is formed. So in order to do this, again, we will take it first and foremost from the points themselves that are of course domain elements inside the complex function. Now, for some interesting concepts, you would have that for each complex number z0, we can find some set of points that will huddle around z0, such that those points would be at, of course, uneven distances away from z0, right? Now, within this cluster, we can find or we can create a particular region that covers every single cluster around z0. We can call this cluster or this region a neighborhood of z0, right? So think about it like your normal communities you have around you, and then for instance you have your nuclear family and it's a cluster around you, and then your house is in a particular street to which that street forms a cluster around your house. You call that a neighborhood, correct? Right? And then you have people within that street to which you are familiar with, and they form a cluster around you as well, which means that your definition or your instances of the neighborhood is dependent on how large you want the cluster to be. Now, in this case, for instance, if we set that the distance between z0 and the maximum possible stretched point in this cluster is, for instance, the radius epsilon, then in this case, we can say we have represented an epsilon neighborhood of z0, which means epsilon remains the maximum possible distance any of those points could travel away from z0, right? That's your absolute distance. However, within this cluster, you would have some points. Let's say there's a point here, let's say z1, such that the distance between z1 and z0 will be completely less than epsilon, because z1 is not at the farthest possible distance, right? I give you an example. For instance, let's say you have yourself an extended family such that the head of the family, the current head of the family, is your grandfather. Now, you as a grandkid to your grandfather would represent the maximum possible distance within that cluster. However, within your father and your grandfather, the distance between them is shortened, right? Because your grandfather gave birth to your father, right? So the distance between them is shortened compared to you that you were given birth to by your father, who was given birth to by your grandfather, which makes the distance longer. That's exactly what's going on here. So you have a point that's at the farthest distance away from z0, such that the distance between them is epsilon, that's your radius. And then you have a point, a random point that does not cover that same distance, that is within that cluster as well, right? So in this case, you could define and say that the absolute distance between that point z1 and z0, right, would definitely be less than epsilon, because it's not at the farthest possible point. So this creates that perception of an epsilon neighborhood. And of course, you could in fact be arbitrary in nature and be like, for any point within this cluster, you could have that z minus z0 would be less than epsilon. And then if you apply, of course, the property of the absolute value, we could split this inequality into minus epsilon strictly less than z minus z naught strictly less than epsilon, such that if you were to add z naught to all sides, you would have this to be z naught minus epsilon strictly less than z strictly less than z naught plus epsilon. And what have we done? We have been able to create an interval around z naught, around z, which is based off z naught. In this case, we can say that z is completely contained in z naught minus epsilon, z naught plus epsilon. And this is very, very interesting. So this tells you that z is interior to that cluster, which is, of course, having a radius of epsilon and then a center at z naught. So this is very, very important. If you're in courses like real analysis, you would call this, of course, an open interval, which it is, and you would also liken it to an open ball. However, we just want to focus more on this fact that this is an epsilon neighborhood. And of course, the neighborhood can shrink more and more, right? And hence the reason why we call it epsilon neighborhood. The neighborhood can shrink more and more. As you get closer and closer to yourself, the cluster shrinks. And it happens in family as well. Yes, we've said the extended family where the maximum distance between you and your grandfather is the largest distance. But then within that extended family is the nuclear family, which is your family, which is to which the head of the family in that case is your dad or your mom, as the case might be. In this regard, that cluster will now be smaller than your extended family. And then you could have a smaller cluster within the nuclear family, which would probably be a cluster around just the kids, to which the head of that cluster will now be the eldest kid in the family. In that regard, of course, that would form a smaller cluster compared to the nuclear family, which is a smaller cluster compared to the extended family. So that is exactly what happens when we consider the neighborhoods around a particular point. So this is very, very important to keep in mind. Now that we have been able to look at this, we could also now use this concept to now create a set of parameters that can arise. Let's say now we now have, of course, this is just around a single point. So what if we now have a collection of those points, right? Such that that collection of points has created for us a sequence of complex numbers. Of course, z0 is a complex number. So if you create a sequence of complex numbers, is there a way in which we can realize or find where that sequence will converge to? The answer is yes. We could find the convergence of a sequence of complex numbers. So we have looked at the neighborhood of a particular complex number. Let's look at what happens when we take the limit of a sequence of complex numbers. So now, in the case of this, let us consider, let's have ourselves a proper sequence Zn, right, as a sequence of complex numbers. Now, of course, if it's a complex number, it means that we can obviously split Zn into xn plus I yn, right, where this will be the real part of the sequence and this will be the imaginary part of the sequence. Then we say that that Zn will converge to a particular limit if we have that the limit as n tends to infinity of Zn equals L. So in this case, we have said the limit of Zn is L. So if the sequence converges, then to converge to its limit. Now, this is very, very important. Now, in this case, we can also write it in terms of the real part of the sequence and the imaginary part of the sequence, and write it as the limit as n tends to infinity of xn plus Iyn is x plus Iy. Such that, of course, we are saying the real part will converge to x and then the imaginary part will converge to x. Now, this is very, very interesting to note because, of course, it implies that we could write this as the limit as n tends to infinity of xn plus I the limit as n tends to infinity of yn being equal to x plus iy. And this is true from our concept of real analysis. So since, of course, zn is equal to xn plus yn, and then limit of zn is equal to L, and we are saying the limit of xn plus iyn is equal to x plus iy, then it means that we can say that L, which is the limit of the complex number, or the series of, or the sequence of complex number, can be equal to x plus iy, right? Which would mean, of course, that the limit as n tends to infinity of xn is x, the limit as n tends to infinity of yn is y. Now, this is very, very interesting. And this represents the limit as it is. So what this is saying in essence is that if you're looking for the limit of sequence of complex numbers, it suffices for you to find the limit of the real part of the complex number and the limit of the imaginary part of the complex number. If you are unable to find the limit of one of those parts, then it would mean that you would not be able to find the limit of the complex number or the sequence of complex number in total. So this is very, very important. Similarly, it can also be looked at in another form, that if you want to find the limit of a complex number, you can just find the limit of the real part and the limit of the imaginary part and then bring that together. That also works as an alternative. Now, if we were to write this rigorously mathematically, we could write it in the epsilon n definition and say that for the limit, right, which of course talks about the convergence of the sequence, in this case, we can have that for epsilon greater than 0, there is a particular value that is positive, such that the absolute distance between the sequence of complex numbers and its limit is very, very small whenever the terms of the sequence exceeds that particular number. So the sequence will converge to a particular limit L if there is a particular value or number such that whenever the terms exceed that number, the difference between the sequence and its limit is almost insignificant, right? It's not 0, it's greater than 0, it's positive, but then it's almost infinitesimal. And this is very, very interesting. So you're saying that if you have, like, say, Z1, Z2, Z3, Z4, there's a particular term you get to, let's assume maybe Z10,000, so that the Z10,001 term is very, very similar to L, right? And from there onwards, you have your terms becoming L, right, at that particular instance. Of course, approximately. So this is what the limit of a sequence of complex numbers talk about. So when we have created and we have discussed the neighborhood of points as well as the limits of the sequence of complex numbers, what happens when those points are now placed into what we call functions? What kind of functions are they going to form? And then how can we discuss the continuity and differentiability of those kinds of functions? This is what we are going to consider in the next video. As always, make sure to like, share, and subscribe. Turn on your notifications to ensure that you do not miss out on any of our content.